All right, section 5-3 is on the formal definition of antiderivative and indefinite integral. The objective of this section is to evaluate antiderivatives and indefinite integrals using the formal notation. Now, if you recall, we've talked about the 4 topics of calculus that we're going to cover throughout the entire year. It's going to come down to one of 4 topics that we're always dealing with. The first was limits, and we learned that a limit is really just a y value. That's what we covered in chapter 2. The second topic was derivatives, and we learned that a derivative was just a slope, and we talked about those in chapters 3 and 4. And the third topic was definite integrals, and we were introduced to those briefly in chapter 1, and we learned those were just area under a curve. And the fourth topic was an indefinite integral, and we're going to obviously dive into that here in this section. All right, so let's start out with just a quick definition here of what an indefinite integral is. And very simply, an indefinite integral is just an antiderivative. And you've actually worked with antiderivatives already, so technically you've already seen indefinite integrals. We just haven't been using that term to describe them. So an antiderivative is just an indefinite integral. So problems like that where you were given f prime of x and then asked to find what f of x would equal, you were finding an antiderivative, or as we see here, it's the same as an indefinite integral you're evaluating. All right, let's talk about the formal notation that we're going to use. As part of the objective was to use the formal notation. Here is the indefinite integral notation. That if I want to find the indefinite integral of some function, this is the way we're going to write it. We have this integral sign, which I'll just reveal this so you can see the names of each of these. We have the integral sign there. That's actually looks kind of like a stretched out S is kind of what it's supposed to look like there. But that's the integral sign, and that means that we're going to find the indefinite integral of this function f of x, or if you will, the antiderivative means the same thing of f of x. F of x is what we call our integrand. So the function you're integrating is called your integrand. And finally, dx, we actually talked about that in the last section there. That's the differential of x. And this is the reason why we had that discussion in the last section first, because of the fact that when we write an indefinite integral in its formal notation, you'll notice that you have a function times a differential of x. That's the way we write it. So it's important you understand what exactly that represents, and how to solve problems that involve a differential times some function. All right, so that's our formal notation. So let's take a look at an example here. Let me just get rid of that. And we're going to use that formal notation here in our example, just a very simple example of integrating x to the 5th dx. Now again, indefinite integral here means antiderivative, so this is kind of like them telling us that f prime of x is equal to x to the 5th, and we want to find the antiderivative or the indefinite integral of that. So the way that we write that, the integral of x to the 5th dx is equal to, basically all I have to do is focus on the function here. I can kind of ignore the integral sign because that's just saying find the antiderivative or the indefinite integral, and I can kind of ignore the dx, similar to the problems that you saw in the last section where they gave you dy that had some function times dx, and you basically kind of got to ignore the dx part and just focus on the function and find its antiderivative. That's the same thing we're going to do here. So since it's a power function, I know that I add 1 to the exponent, so it's x to the 6th. I have to multiply by the reciprocal, or really I'm dividing by that exponent, if you will, but multiplying by 1/6 is the same thing. And then add c to that. Okay, so there's how we would evaluate this indefinite integral here. Again, the nice thing about this notation, they don't have to write down f of x, or I guess they would write down dy in this case is equal to x to the 5th dx. Rather, I just use this symbol here, and it means find the indefinite integral. Similar to how you have a notation that means find the limit, that LIM notation, or a notation that we use to indicate find the derivative, that d over dx. Means the same thing there, or it has the same idea as this. Okay? So there's the formal notation. All right. The definition, the formal definition here of an indefinite integral is this, and actually there's two ways to define this, and so we'll look at each of those. And the first definition here says this, that g of x is equal to the indefinite integral of f of x dx, or the antiderivative of f of x, however you want to read that, if and only if the following is true, that g prime of x is equal to f of x. So in other words, you can say that g of x is the antiderivative of some function as long as when you take the derivative of g, that turns out to give you f of x. Now, if you think about this here carefully, this is exactly how we said you can check your answer when you believe that you've come up with an antiderivative. If you think you've got the equation that's your antiderivative, g of x, we say that the way that you check your answer over here is take the derivative of g and see if you end up with the same function that you started with over here. See if you end up with f of x. That's all that's saying. So in other words, we've done this already. The formal definition of an indefinite integral is actually what we are using as our way to check or to verify that our answer was correct. Now you can rewrite that slightly, and depending on what you're doing here, depends on which one of these definitions might be easiest for you to write or might make most sense for you to work with. The second way to write this would be to say that g of x is equal to the indefinite integral of f of x dx. Same first part, if and only if. But now instead of saying g prime, notice that we're going to replace basically g prime of x with this. This is saying the derivative, d dx, of the indefinite integral of f of x dx is equal to f of x. The integral of the, the derivative of the antiderivative of f. And this is the reason why it turns out to be equal to f of x, because of the fact that the derivative followed by an antiderivative basically gives you back what you started with. Or actually, it's the other way around, that you're first finding the antiderivative of f of x, and then you're following that up with a derivative. You're working on from the inside out there. But nonetheless, that's another way that we can write it. Okay, g prime of x is the same as the derivative of the integral of f of x dx. All right, here's a couple of properties here that you should know working with indefinite integrals. And in fact, some of these properties will start to sound familiar, hopefully, because of the fact that we've talked about similar properties with limits as well as with derivatives. And it turns out with indefinite integrals, we have some similar properties here. So the first one is for the indefinite integral of a constant times a function. So it turns out that if you have the indefinite integral of k times f of x dx, k is some constant, so you've got a constant times a function, that turns out to be equal to k times the indefinite integral of f of x dx. In other words, the constant can be brought out front. Just like finding a derivative, you can, that constant out in front stays out in front when we take the derivative. Same is true with a limit, and it turns out the same is true here with an indefinite integral. Okay. The second property here is for the sum of two functions. And just like with limits and derivatives, we had a property for the limit of a sum of functions, or in the derivative of a sum of functions. We have a similar property here for the indefinite integral of the sum of two functions. And so this says that the indefinite integral of f of x plus g of x dx is equal to the integral of f of x dx plus the integral of g of x dx. In other words, the indefinite integral of a sum is equal to the sum of the indefinite integrals. Basically, we have the same verbiage there talking about limits. The limit of a sum is equal to the sum of the limits. And the same was true with derivatives. The derivative of a sum is equal to the sum of the derivatives. Same thing is true here. The indefinite integral of a sum of functions is equal to the sum of the integrals of the functions. All right. Let's take a look at an example here and try using these properties. So example 1. Example 1 says to evaluate 5 cosine of 5x plus 3 dx. All right. So the first thing to recognize here is that I've actually got a constant times a function. So we might as well use that first property that we just looked at, that the integral of a constant times a function, the constant comes out front. And I would say probably at first that might be helpful to do that first step, but probably eventually you'll get to the point where you don't necessarily need to rewrite it. But nonetheless, the constant can come out front and basically does not affect the indefinite integral here. And now we've got the indefinite integral of cosine of 5x plus 3. Now that's a composite function. So in order to end up with this, we must have started with a composite function so that the derivative turned out to be this guy. So in order to find the antiderivative, or the indefinite integral, I've got to think of chain rule and kind of go backwards from there. All right, so the constant stays up front. And let's deal with this composite function. Now I know that chain rule says you take the derivative of the outside function first. So I must have taken the derivative of some function and ended up with cosine. So I must have started out with sine. So it must have been the sine function that I took the derivative of to get cosine. And then secondly, chain rule says that you substitute in the inside function. So the inside function that I have right here must be the same inside function that I have in my antiderivative. So this must be 5x plus 3. All right, so again, we've taken care of the first two steps of chain rule. I've taken care of the derivative of the outside function. Derivative of sine will give me cosine. I've taken care of substituting in the inside function there, the 5x plus 3. The last piece that I need to deal with is the derivative of the inside function. Chain rule says we multiply by the derivative of the inside function, but again, since we're finding the antiderivative here, instead of multiplying by that derivative, we've got to divide by the derivative of the inside, or I'm going to multiply by the reciprocal. So the inside function is 5x plus 3, its derivative is 5, so we need to divide by 5 or multiply by 1/5. And finally, we need to add c onto the end of that. Of course, anytime we find an antiderivative, we always have that constant of integration, that plus c at the end. And here we've got 5 times a 1/5, so those guys will cancel out. We end up with just sine of 5x plus 3 plus c. All right, and again, as the definition, the formal definition of an indefinite integral said, that if I'm calling this the antiderivative, we'd said that's g of x in that definition, then if I take the derivative of this, I better end up with the function that I started with. So let's just quick check that and see if that in fact is the case. So here's our check. I want to take the derivative of the following with respect to x. It's the sine of 5x plus 3 plus the c. I want to take the derivative of that and see what we end up with. So the derivative of a composite function, derivative of the outside function is cosine. Chain rule says you substitute in the inside function. That's the 5x plus 3. Then we multiply by the derivative of the inside, which is 5. And of course, the derivative of our constant there at the end is 0. So this turns out to be 5 cosine of 5x plus 3. And if you go back to what we started with 5 cosine of 5x plus 3. Now we found the derivative of it. If you wanted to find the differential, you could get the dx at the end there, but as long as we get the same function there, the same integrand, we are pretty good. All right? Now, if you struggle with that problem and have trouble coming up with the constants that show up in that problem, and you can even use this for other reasons, but if you have trouble seeing how to find that antiderivative, one thing you can do to help yourself out is use this technique right here. There's actually going to be a number of techniques we'll learn throughout the course of the year to help us evaluate indefinite integrals or antiderivatives. Those are the ones that are not very easy to evaluate, so we need some different techniques we can use to help us do it. This is one of those. It's called a variable substitution. It's also known as a u substitution because the fact that the variable we use to substitute is u. So therefore, it's a u substitution. All right. So the way that we use a variable substitution is you use a variable substitution to make the problem easier. And basically what we're going to do is we're going to take part of the problem and replace it with just a single variable. And hopefully, and by doing so, we've made the problem easier. Obviously, if you've made the problem more difficult, then go back to the original. The goal here is to make the problem simpler, not more difficult. Okay, so if after attempting a variable substitution, you look at it and go, well, that's a lot more difficult than what I started with, then back up. Okay, so let's go back to this example that we just did and see how we could use a variable substitution to help us evaluate that. Now, the way that you use a variable substitution, at least for right now, what you're going to find works is if you have a composite function, like we have right here, cosine of 5x plus 3. I have gotten rid of the 5 here, so I changed the problem slightly. But I have the cosine of 5x plus 3, where if the 5x plus 3 is the inside function. And for right now, that's going to be your choice for u. Basically, when you have a composition, you want to make the inside function u. So I'm going to say u is equal to 5x plus 3. Now, you can see that I can easily then replace the 5x plus 3 with u, but the problem is that I also have a dx in here. If I'm going to do a variable substitution, I have to get rid of all of the x's, and I have to replace them with all u's. So I need to find out what dx is equal to, is in essence what I'm trying to find here. But the way to do that is to find the differential of this equation I have over here for u. So find the differential of u. Du is equal to, the way you find a differential is you take the derivative of your function. Derivative of 5x plus 3 is just going to be 5 times your differential, the dx, differential of x. And again, I'm trying to find out what dx is equal to, so let's move the 1/5 over to the other side. Basically, this is fine to do as long as you're moving just a constant over to the other side. If it's not a constant, keep the u's on one side and the x's on the other side. Don't move x's from one side to the other. But there's what the value of dx turns out to be equal to. So now I could do my substitution. I could rewrite this as the integral of the cosine of, instead of 5x plus 3, that's the cosine of u, times dx, and instead of dx, I'm going to replace that with the 1/5 du. Now I'm going to use our property here that says if we have the integral of a constant times a function, I can bring the constant out front, so that's the integral of, or 1/5 the integral of cosine of u times du. And now at this point, before you start integrating, stop and look at this and determine whether you've simplified the problem or not. If you go back to the original, is it easier to integrate cosine of 5x plus 3, or is it easier to integrate the cosine of u? If you've made the problem simpler, then continue on. Find the antiderivative and be done with this. If you've made it more complex, then go back to the original. But we've definitely simplified this. I know the antiderivative of cosine of u. That is, I know that to get a function whose derivative is cosine, I must have started with sine. And with an antiderivative, we always, of course, have our plus c at the end. The only thing that I have a problem with this answer is that I started out with an equation that was in terms of x. I end up down here with an answer that's in terms of u. So I need to replace u with what it's equal to, but up here I told you u is equal to 5x plus 3. So we can just simply substitute that into our answer down here, and we'd end up with 1/5 the sine of 5x plus 3 plus c. Okay? Again, if you're having trouble with seeing where this 1/5, those constants show up, the nice thing about this process is realize that the 1/5 just showed up right here. I didn't have to really try to figure out where the 1/5 is going to come from. It just showed up in the problem, and so it automatically brings that in by using a u substitution like this. Okay? We'll use that on the next example here. Look at example 2. Example 2 says to integrate 7x plus 4 to the 9th. All right, and again, I'm going to use a variable substitution to do this. So when you see a composition, look at the inside function and make that your choice for u. Now, as we get going here and the problems become more complex, there'll be some other techniques we talk about as far as how you pick this value u. But for right now, with a composition, you can pretty much bet on the fact that the inside function is what you want to make u equal to. And let's go ahead and calculate what du is equal to. Derivative of 7x plus 4 is 7 times dx. And again, I just want to know what dx is equal to, so let's move the 7 to the other side. 1/7 du is equal to dx. So now I've got my substitution. I can plug that in. So instead of 7x plus 4 to the 9th, it's u to the 9th. And instead of dx, dx is equal to 1/7 du from our substitution over there. Again, I'm going to go ahead and slide the 1/7 out front. That's just a constant, so we can bring the constant out front, remember. U to the 9th du is what we're integrating. Again, go back to the original. the integral of 7x plus 4 to the 9th dx, and compare that with our substitution here, 1/7 the integral of u to the 9th plus or times du. If you've simplified the problem, keep going with it. If the problem looks more complex, go back to the original. Definitely looks like we've simplified it, so let's keep going. The 1/7 stays out front. Follow your power rule here for integrating u to the 9th. Again, you add 1 to the exponent, so it's u to the 10th. You multiply by the reciprocal, 1/10, or divide by 10. And of course, we always add on c at the end with an antiderivative. And then finally, replace u with what it's equal to. I'll go ahead and combine the 1/7 and 1/10. That's 1/70th. And then u, remember, was equal to, this value u right here, was equal to 7x plus 4 up there. So I'm going to replace that with 7x plus 4 to the 10th plus c. Again, the nice thing about that, if you're looking at this problem going, how did they get 1/70th? Realize it came in because of the fact that the 1/7 showed up because of this differential over here. And the 1/10 part of it came in because of the fact that you're using power rule. Okay? But if you're struggling with seeing where that constant comes into play or how it shows up there, using that u substitution will definitely help you with that. All right. There are a couple of properties here. We've used them actually in a couple of our problems here. In fact, we just used this one, but just so we know what our properties are for some functions we've already learned how to find the derivative of, let's refresh our memory from as far as how we find the antiderivative of them. Again, remember that anytime you find a derivative, you at the same time you've learned an antiderivative. Take the answer you came up with that derivative, and its antiderivative is the function you started with. All right, so the power function here, if you integrate x to the nth dx, that turns out to be 1 over n plus 1 times x to the n plus 1 plus c. Again, you add 1 to the exponent and then divide by that exponent. And of course, you add c onto the end. And for exponential functions, if you integrate b to the x dx, that's equal to 1 over the natural log of b times b to the x plus c. And if it's e to the x, again, the nice thing about e to the x, it's its own derivative, so therefore it's also its own antiderivative or indefinite integral. The integral of e to the x dx is e to the x plus c. All right? Now, the nice thing about these power functions and exponential functions, obviously there's a big difference between the two. But if you look at the rules that we use for derivatives and the rules that we use for antiderivatives as far as the constant is concerned, it looks very similar. Let me just remind you of that if you take over here on the left here, the derivative of x to the nth is equal to n times x to the n minus 1. That's your rule for the derivative of a power function. If you look at the derivative of an exponential function, the derivative of b to the x, remember, is equal to the natural log of the base times b to the x. Now the similarity here is this. Notice that in both cases with the derivative, you end up multiplying by some constant out front. And you multiply, in this case, it's almost identical to the original function in the case of a power function. In the case of an exponential function, it's exactly the same as the function you started with. Those are very similar if you look at it in terms of just a constant times some function. Now, if you look at the antiderivatives, it's very similar as well. In the case of the antiderivative, look again that first of all, you're dividing by some constant for the power function. You're dividing by n plus 1 or multiplying by the reciprocal. And with the the exponential function, same thing. You're dividing by some constant, the natural log of b. And then in both cases, again, you're multiplying by some function that's very similar to what you started with. In the case of a power function, it's x to the n plus 1. And in the case of the exponential function, it's the exact same function you started with, b to the x. Okay, if you remember the similarities there between those two, it might help you remember the rules. Definitely important that you remember the rules there for the derivatives of these two functions as well as their antiderivatives. And so this might help you remember those. All right, so let's try using those in a couple of examples. Look at example 3. Example 3 is the integral of e to the negative 2x dx. Now again, I'm going to use this u substitution on this thing to help me evaluate it. If you look at the negative 2x, that's the inside function. So that's my choice for u over here. U is going to be a negative 2x, which means du is equal to a negative 2 times dx. Derivative of negative 2x is negative 2 times the differential of x, dx. And again, I want to know what dx is equal to. That's what I have over here. So let's divide by the negative 2. It'll be a negative 1/2 du is equal to dx. And now we can make our substitution. So we end up with e to the, instead of negative 2x, it's e to the u times dx. And instead of dx, I'm going to replace that with a negative 1/2 du. Put it in parentheses since it's negative there. And let me pull the negative 1/2 out front. One of our properties there, we said, for the antiderivative or the indefinite integral of a constant times a function, the constant can come out front. And that's e to the u du. And again, at this point, you should go back to the original and see if you've simplified the problem. Is it easier to integrate e to the negative 2x or e to the u? Well, e to the u is really nice because it's its own antiderivative. So negative 1/2 stays out front. E to the u is just e to the u. The antiderivative, I should say, of e to the u is e to the u plus c. And again, the only thing I don't like about our answer here is that it's in terms of u. So I need to replace u with what it's equal to. But if you go back up here, we said that u right here was equal to a negative 2x. So I can just replace u with the negative 2x. So we get a negative 1/2 e to the negative 2x plus c. That is our antiderivative using that variable substitution. And let's take a look at one last problem here, the integral of 5 to the x dx. Actually, we just wrote down the rule for finding the antiderivative. And to help you remember, okay, I know with an exponential function, there's going to be a natural log of the base that's going to show up. But am I multiplying by that or am I dividing by it? Remember the rule for power functions. When I integrate a power function, I have to divide by that exponent. Same thing is true here with an exponential function. When I integrate it, I'm going to have to divide by that log. So it's 1 over the natural log of 5 times the 5 to the x plus c. Here's our antiderivative. All right, and that is the end of the first part of this section.